Let me start the recording. Good morning, grade 8. Okay, as promised, let's move forward now from the perspective of the natural radioactivity, okay, by Barraquel and Ernest Rutherford. Let's move now to Rutherford's nuclear model of an atom. What's with Rutherford's nuclear model of an atom? What's with it? Okay, Rutherford studied alpha particles. As we discussed about the natural radioactivity, we actually tackled about the three particles. The first type are considered as positively charged, which we are actually called, or which they are called alpha 8 or alpha particles, alpha rays. Okay. Second type is the negatively charged, which is the beta or beta rays, or the alpha is the positively charged. This is the protons. Beta is considered as the negatively charged, or this is the electrons. And of course, the third type is uncharged, meaning to say this is neutral, okay, called the gamma rays, which is considered as the neutron. Okay, let's take a look at Rutherford's nuclear model of an atom. He used this to test, okay, Thomson's model of an atom. The J.J. Thomson's model of an atom is the one that has a pudding. It looks like a plum pudding. Are you familiar with plum pudding again? Bread, raisin bread, a bread with a lot of raisins inside. So that is actually the concept of J.J. Thomson. Okay, he used alpha particles as bullets to fire at the gold foil and see what happened. So this is now the experiment of Ernest Rutherford. Okay, the result seen as small flashes on a fluorescent screen. From the result of this experiment, Rutherford concluded that there must be a small and massive center inside each gold atom. Inside the gold atom, right? That was positively charged. That is actually the protons. This explained why a few alpha particles bounce right back toward the source. He also concluded that an atom must be mostly empty space to explain why most alpha particles went straight to the gold foil. Okay, this is now the experiment of Ernest Rutherford. Okay, he actually uses what, a gold foil and a screen, okay, detecting screen. So upon checking, he actually used the alpha particle emitter. He emits the alpha particle towards the gold foil, and in his experiment, he concluded that again there is a positively charged particles acting on it, okay, in an empty space. Okay, so the atomic model of Rutherford talks about the central nucleus. Okay, the structure of the nucleus and the neutron. Since Rutherford already already found out that there is a central nucleus. There is a central nucleus on that certain element. Rutherford experiment opened the door for the investigation of the nucleus. Okay, he found that the number of positively charged or positive charges in the nucleus increases from atom to atom by single unit when the elements are arranged consecutively. This means that the nuclear charge is the basis of atom's individuality. How individual the atom is, how separated the atom is, this is now the basis. Okay, it is because of its nucleus. So we can actually distinguish them based on their nucleus. Rutherford also established that the positive charge is due to the presence of fundamental particle called protons, or positively charged element or particle. Okay, do you have any questions so far? Just let me know if we are too fast, and please ask questions. I cannot see someone or somebody turning their camera on. Again, please turn on your camera, everyone, so that I can see you. And please do ask questions if in case. All right. The atomic number, which is designated as Z of an element, is the number of protons in the nucleus. Again, the atomic number. Okay, let me share my screen. The atomic number, which is designated as D of an element is the number of protons in the nucleus. So if you're going to have your periodic table of elements, let me share my periodic table of elements. I will let you see where you can find your atomic number. Okay, hold on. If this is your periodic table of elements, make sure that you have your periodic table of elements with you. Okay, because this will be included in your exam. If this is your periodic table of elements, okay, where can you find your atomic number? Okay, always and always consider again you need to consider the what? The legend, because not, okay, not all of the periodic table are the same. Okay, they are different, right? So in this case, my atomic number is in the upper left corner of my element. So my atomic number is 13 in aluminum. So my aluminum contains how many nucleus? Or how many protons? Rather, how many protons? It has 13 protons based on the explanation of what? Of Ernest Rutherford. Okay. Again, the atomic number which is designated as Z of an element is the number of protons, number of positively charged particles in the nucleus. Okay. Since an atom is electrically neutral, the number of protons must be equal to the number of electrons. If it is what? If it is neutral, stable, if it is not an isotope. Isotope is different, right? It's a different version of that particular element. And isotope also will give us an idea about radioactivity, how radioactive an element is, right? So again, the number of protons, okay, indicates the atomic number plus it is equal to the number of what? Number of electrons. They're equal, okay? The number of protons is equal to the number of electrons. So if the number of electrons in aluminum is 13, so the electrons there is also 13. If it is not, if it is stable, okay? If unstable is different thing, okay? The discovery of third fundamental particle in 1932 was credited to James Chadwick. This is from 1891 to 1974. He is actually a British physicist. The exclusive particle is called neutrons, the neutral element. It has a mass roughly equal to the proton but has no electric charges. There is no electric charges or electrical charges there since this is neutral. Okay? Since the mass of an atom is concentrated in the nucleus, a mass number designated as A is equal to the sum of masses of protons and neutrons. Okay? Mass number. Where can you find your mass number in your periodic table of elements? Okay? Mass number or atomic mass. Okay? Atomic mass, you can actually find it. Again, check on the legend. So the atomic mass here is in my upper right corner of the element. Aluminum is 26.98. Okay. Let's continue. To calculate the numbers of atomic particles in an atom, use the atomic number and mass number. Okay. Now, the number of protons, okay, this is the atomic number itself. Okay. The number of electrons, how can you check on the number of electrons? The number of electrons is equal to atomic number minus the charge. Okay. If it is negative or positive. Okay. So it will give you the number of electrons. Okay. How about the number of neutrons? The number of neutrons is equal to mass number minus atomic number. Again, the mass of neutrons is equal to mass number minus the atomic number. Okay, please take note of this formula because we'll be using this one all throughout the activity. After this discussion, I'll be giving a lot of series of activities. Now, again, the number of protons is equal to the number of atomic number. The number of electrons is equal to atomic number minus the charge. It could be positively charged, it could be positively charged, or it could be negatively charged. Ions. Okay? Number of neutrons is equal to mass number minus the atomic number. That is your number of neutrons. Sure, you told us that protons and electrons are equal. Yes, correct. Provided that there is no charge there. Okay, these charges will change your electrons. Of course. The protons there are actually what? Actually, there. It's present there without any changes, but if there are some charges, your electrons will be changed. Okay, it's constant. Protons there are constant. In writing chemical symbols of elements, a superscript or the upper and subscript or the lower are often seen on the left side of the symbol. Okay, the superscript refers to the mass number. Superscript, again, mass number. The upper is the mass number, while the subscript or the lower part is the atomic number. Okay, studies on masses of atoms showed that atoms of the same element have different masses. Such species are called isotopes, the one that I'm telling you a while ago. There are some isotopes in particular element. Okay, different isotopes could mean different radioactivity, sensitivity, or radioactive activity, or radioactive decay. So those are just few of the isotopes. Okay, isotopes have different masses or mass numbers. Thus, they also differ in numbers of neutrons. However, the variation of the number if neutrons does not change the identity of an element. This is because isotopes of a particular element have the same number of protons. Take note, your protons again and again is constant. That's the reason behind. Okay, because this is based on your what? In your atomic number. Okay. The discovery of isotope contradicted Dalton's postulate that all atoms or given elements are alike. Yes. That's it. Because, again, there are a lot of studies concluded that there are a lot of isotopes in a particular element. Hydrogen, for example, there are a lot of isotopes. Okay. Some of them are actually used for treating cancer. Some of them are actually used for treating what? Certain diseases. There are about 250 isotopes occurring naturally. More than 1,000 are made in nuclear reactors because, again, this is actually what? This is radioactivity. Okay? Radioactive. Isotopes are found have extensive applications in medicine. Correct. Like, for example, cobalt-60 is used in cancer therapy, while iodine-121 is used for goiter therapy. Imagine that. However, an atom may have a charge. If an atom has more electrons than protons, the species becomes negatively charged. That is what we call as an ion. If an atom has less electrons than protons, the species of the element or the species becomes a positively charged cation. Okay? Anion if it is negatively charged, cation if it is positively charged. Charged species in general are called ions. That is why there is what we call as ionic bonding. Okay, in chemical reactions, in combining chemicals, there is ionic bonding and metallic bonding and so on. So this is because the ions bind with each other. Okay, the cation and an ion. Questions so far? I didn't hear questions from you. Did you get the point of the lesson? Ready? Are you sure? All right, let's continue. The inadequacy of Rutherford's model. It's inadequate. What's with adequate? What's with the flaw? Okay, there is a flaw of Rutherford's nuclear model of an atom. What this major flaw? it conflicted with the previously established theory of electric field proposed by Scottish physicist James Maxwell. What's with Maxwell's proposed theory? Okay, the theory of electric field. When a charged body moves in an orbit around another oppositely charged body, the assembly of the particles will gradually lose energy by emitting radiation. That's actually according to what? According to James Maxwell. The loss of energy would cause the electrons to move in a circle even closer to the nucleus until eventually these electrons will be in direct contact with the nucleus. That is based on James Maxwell's theory of electric field. That's the major flaw of Rutherford's nuclear model. Okay, the dilemma remained unsolved for some time. It was it was a desperate situation when, but Niels Bohr, this is between 1885 to 1962. He is actually a Danish physicist, provided the answer. How did Niels Bohr answer this dilemma? Let's take a look at this. The nature of light. Okay, let's tackle first some of the bits of the information, and let's find out how, again, Niels Bohr answered those dilemmas. Nature of light. Light has always fascinated man. The first scientific study on the nature of light was done by Christian Huygens in 1629. This is between 1629 to 1695. He is actually a Dutch mathematician and a physicist. He stated that the light, like sound, is a wave in motion. Okay. His idea of wave nature of light met the opposition when Sir Isaac Newton, okay, one of my favorite scientists, in between 1642 to 1727, was one of the giant in science who opposed this idea. Newton formulated the corpuscular or the particle theory of light. Okay, this is now the birth of the theory of light, the particle theory of light. According to this theory, light is made up of a very fast and very small particles which travel in straight lines. Okay. Again, according to Newton, that in the particle theory of light, that light is made up of very fast and very small particles which travel in a straight line. Maxwell predicted that an alternating current in a circuit would radiate energy in the form of electromagnetic waves traveling through a vacuum at the speed of light. Okay, Maxwell wrote, if it shall be found that the velocity of propagation of electromagnetic disturbances, is the same velocity of light, we have a strong conclusion for believing that light is an electromagnetic radiation. But again, light is an electromagnetic radiation. Correct. It is already proven. Okay. Here comes Heinrich Hertz. We still have 6 minutes. I think we discussed a lot. We will just stop in Maxwell's prediction. Okay. And let's continue with Heinrich Hertz. Let's find out what are the contributions of Heinrich Hertz with regards to, this is in the frequency. I think Hertz is talking about frequency here. Okay. Based on Maxwell's interpretation. Okay, do you have any questions so far? Still have 6 minutes for interrogation, questions, violent reactions. Any question? You know what, class? I am really worried. In my mind, at the back of my mind, I am really worried if my students would not ask questions. It's either you didn't understand the lesson, number one. Number two, you understand the lesson, okay, and it is clear to you. And number three, you are actually confused. Or number four, you're power driven, overpowered. Okay. Again, I want you to ask questions every now and then, simply because these questions are really interesting, or this topic rather are really interesting. Okay. And you'll be using this one all throughout, even in college and senior high, right? So again, that will be all as of the moment. Let's stop in Heinrich Hertz. Let's discuss Heinrich Hertz by next meeting. Okay. Hopefully you learned something out of our discussion. Okay. We have discussed a lot. right? I think that will all for today, class. Grade 8. Have a nice day. Take your lunch. Bye-bye. Take care.